Good morning. We were discussing about efficient and scalable techniques for frequent item set mining. Simply we can call association mining techniques. We have studied one of the important algorithm known as a priori, uh, which were finding frequent item sets using candidate generation. We have studied the algorithm in detail with an example. We have generated one frequency, two frequency, then candidate set generation we have seen, and the pruning step we have seen, and based on these frequent item sets we have generated some rules with minimum support and confidence, which are known as association rules. By this session we will study some more techniques. First one is mining frequent item sets without candidate generation. We have studied a method using candidate generation. Now we are going to study about a method that are not using the candidate generation. It is known as FP growth algorithm. Then we will discuss about mining frequent item sets using vertical data format. And one more technique is based on mining closed frequent item sets. So these are included in this particular session, and these are frequent item set mining methods, or we can simply say association mining techniques. First one is mining frequent item sets without candidate generation. The a priori candidate generate and test method significantly reduces the size of candidate sets, leading to good performance gain. Okay, we have seen how to improve the efficiency of a priori algorithm. It can generate and test method, candidate generate and test method can be used to reduce the size of candidate sets. The size of candidate sets is one of the disadvantage of a priori algorithm, but we can reduce that size, and then it will perform well. However, it can suffer from two issues. These are two issues still there with a priori algorithm. It may need to generate a huge number of candidate sets. It may need to repeatedly scan the database and check a large set of candidates by pattern matching. These are the two issues still having with a priori algorithm. An interesting method in this attempt is called frequent pattern growth, that is abbreviated as FP growth, which adopts a divide and conquer strategy. So we are adopting a different strategy for FP growth algorithm, and it will avoid these issues regarding a priori algorithm. FP growth algorithm is also a two-step process like a priori. First step is it compresses the database representing frequent item sets into a frequent pattern tree, that is known as FP tree, which retains the item set association information. And the second step, it then divides the compressed database into a set of conditional databases. These conditional databases are known as special kind of projected database. Each will be associated with one frequent item or pattern fragment and mines each such database separately. So these are the two steps involved in FP growth algorithm. First, it compresses the database and it will form a FP tree. Then it will divide the compressed database into a set of conditional databases. We will study the FP growth algorithm using example. The first scan of the database is same as a priori, which derives the set of frequent items, that is one item set, and then support counts. Let the minimum support count be 2. The set of frequent items is sorted in the order of descending support count. We are here seeing the set of frequent item sets in descending support count order. This resulting set or list is denoted as L. Thus we have L equal to, here we have item 2, item 1, item 3, item 4 and item 5, and item 2 is having support count of 7, that is the highest support count value. So we have represented that first, then I1 with support count 6, then I3 with support count 6, and I4 with support count 2, and I5 with support count 2. So these are represented in a descending order. Descending order based on the support count. An FP tree is then constructed. First we will represent like this, then we will generate or construct an FP tree after scanning all of the transactions as shown below with the associated node links. So see the figure, an FP3 tree registers compressed frequent pattern information. Here we have a item ID list with support count, and also we will have node links in this table. So we have generated one FP tree based on the support count, and these are doing by scanning all of the transactions that we will see by the next slides. So this is one of the example of representing an FP tree, how it is represented. You can see here we have started from null set, then we have item 2 is with the highest support count value, and we have started from there, and we have also the I1 next highest value is with I1, that is also represented in this particular tree. Then I2 and next level we have I1 that is with support count 4, and I3 with a support count 2, I4 with support count 1 in the left subtree, and in the right subtree we have I3 with support count 2 under the I1 with support count 2. This is an example for representing an FP tree based on the support count by scanning all of the transactions given. Okay, we will see how these are represented and how we can use this FP tree for frequent item set mining. The FP tree is mined as follows. We will see how it is mined. Start from each frequent length 1 pattern. First we will start from each frequent length 1 pattern, that is frequent 1 pattern, as an initial suffix pattern. We are considering it as initial suffix pattern. Then construct its conditional pattern base. Then we will construct its conditional pattern base. First we will generate frequent 1 set like a priori. Then we will construct a conditional pattern base, that is known as subdatabase, which consists of the set of prefix paths in the FP tree co-occurring with the suffix pattern. We will understand by considering the example. So just listen what are the steps involved. Then construct its conditional FP tree. Then we will construct a conditional FP tree, then perform mining recursively on such a tree. The pattern growth is achieved by the concatenation of the suffix pattern with the frequent patterns generated from a conditional FP tree. So we will see the example that is shown in table 5.2, mining FP tree by creating conditional pattern bases. Here we will start with the highest support count value, that is we will start with I5. I5, what are the conditional pattern base here? We can see by the example. We will start from I2, and then it will lead to I1, and we have a support count of these two frequent pattern, that is 1, and we will have another pattern condition base, that is I2, I1, I3 with a support count 1 that will lead to the I5. Okay, so these are the conditional pattern base for I5. Item 5. Then we will generate a conditional FP tree. In this, by seeing the conditional pattern base, in this two combination or two patterns we have I2. So we will count it as 2. So I2 is coming for the 2 times. So the support count is 2 here for I5. Then I1 we will see. I1 also coming in 2 sets of the conditional pattern base. So the support count is 2. But I3 support count is only 1. So we will not consider that. Okay. Then we will generate frequent patterns with I5. So we will generate I2, I5, and we will see the support count, that is 2, and I1, I5, that is also support count 2, and finally we have I2, I1, I5, that is 2. So these are the steps involved in finding the frequent patterns using the FP tree. So we have seen an FP tree in the previous slide, and based on the patterns or the node links, we have generated this conditional pattern base first, then conditional FP tree, then finally we have generated frequent patterns based on this. Okay, like the same we have generated, we have to consider I4, I3, I1, etc. And while we consider I4, we should not consider I5 again, because we have considered I5 in all the sets. So it should not be repeated in the coming items combinations. So we will not consider the previous case. Like that, I3, when we consider I3, we will not consider I4 and I5 again. Like that, we have generated the FP tree by creating conditional subpattern bases. The same procedure is explained in this particular slide. We first consider I5, which is the last item in L rather than the first. The reason for starting at the end of the list will become apparent as we explain the FP tree mining process. I5 occurs in two branches of the FP tree of figure 5.7. The occurrences of I5 can easily be found by following its chain of node links. So we are observing that by the chain of node links, the paths formed by these branches are I2, I1, I5. That's why we have seen I2, I1 as the conditional base, and I2, I1, I3, I5, that is also with support count 1. Therefore, considering I5 as a suffix, its corresponding two prefix paths are I2, I1, 1 and I2, I1, I3 with support count 1, which forms its conditional pattern base. Its conditional FP tree contains only a single path, that is I2 with support count 2 and I1 with support count 2. I3 is not included because its support count of 1 is less than the minimum support count we have considered. The single path generates all the combinations of frequent patterns, that is I2, I5 with support count 2, I1, I5 with support count 2 and I2, I1, I5 with support count 2. Similarly, for I4, I3 and I1, for I4, no need to consider I5 again since already considered, and so on. So this is once again explained using this particular slide, and you can add these points while you explain the example. So we will see what are the advantages of FP growth algorithm. This method transforms the problem of finding long frequent patterns to search for shorter ones recursively and then concatenating the suffix. It uses the least frequent items as a suffix, offering good selectivity. So we are considering it backwards. So it will offer good selectivity. The method substantially reduces the search cost. When the database is large, it is sometimes unrealistic to construct a main memory based FP tree. An interesting alternative is to first partition the database into a set of projected databases and then construct an FP tree and mine it in each projected database. The performance of the FP growth method shows that it is efficient and scalable for mining both long and short frequent patterns and is about an order of magnitude faster than the a priori algorithm and one more algorithm that is known as tree projection algorithm. So FP growth algorithm performs well rather than a priori and tree projection algorithm. So these are the advantages of using FP growth algorithm. Now we have studied two important techniques that are a priori and FP growth algorithm, and we will introduce two more techniques for frequent item set mining, that are mining frequent item sets using vertical data format and mining closed frequent item sets. I will introduce these concepts in a short manner because usually the topics asked in this particular session is from a priori algorithm or maximum it will ask for FP growth algorithm. So we will see what are the two more techniques that are mentioned as per the syllabus. That is, we should not go into the depth because the main points you will skip, otherwise you have to study the important techniques. So I will just mention the main points here and we will see some example also in a very short manner. So let us discuss about mining frequent item sets using vertical data format. Both the a priori and FP growth methods mine frequent patterns from a set of transactions in transaction ID item set format. We have seen a format that is type transaction ID then item set. So we have seen such examples where TID is the transaction ID and item set is the set of items bought in transaction TID. This data format was known as horizontal data format. Alternatively, data can also be represented in item ID set format. So we are representing the data in a different format that is known as vertical data format. Here first we will represent item then transaction ID. So for particular item, how many transactions we will have to represent, that is represented in GID set. So this format is known as vertical data format. This is used in one algorithm known as equivalence class transformation, in short ECLAT algorithm. So this is a particular method that is having a different representation of the data. Example for vertical data format representation by scanning the given dataset once. So here we have to scan the database only once. That is the advantage of representing this particular format. You can see the example in table 5.3. Here we have 5 item sets, that is 1, 2, 3, 4, 5. And item 1 is coming in transactions, transaction 100, transaction 400, transaction 500, 700, 800 and 900, so on. So item 2, then item 3, these are the representation in this vertical data format. Now this is a frequent 1 item set. Then we can represent frequent 2 items and the particular vertical format, and the 3 item sets also can be represented in vertical data format. These are the vertical data format representation. We will see what are the advantages of using this particular method. Besides taking advantage of the a priori property in the generation of candidate item set from frequent k item sets, it is taking the advantage of a priori algorithm or a priori property, and we have another merit of this method, that is, there is no need to scan the database to find the support of k plus 1 item sets for k greater than or equal to 1. We should not want to scan the database again and again here. So that is the one advantage of using this particular data format. However, the transaction ID sets can be quite long. Here, the transaction ID sets can be quite long, taking substantial memory space as well as computation time for intersecting the long sets. To further reduce the cost of registering long TID sets as well as the subsequent cost of intersections, we can use a technique called diff set, which keeps track of only the differences of the TID. I'm not going to discuss it in detail. You just understand the diff set method can be used for avoiding the memories utilization as well as the computation time for inserting the long sets. These are the advantages of using vertical data format. Next one, we are going to study about mining closed frequent item sets. From the set of closed frequent item sets, we can easily derive the set of frequent item sets and their support. Thus, in practice, it is more desirable to mine the set of closed frequent item sets rather than the set of all frequent item sets in most cases. So, we have to see what are the closed frequent item sets rather than finding all frequent item sets. A naive approach would be to first mine the complete set of frequent item sets and then remove every frequent item set that is a proper subset of and carries the same support as an existing frequent item set. However, this method is quite costly. So we will see how we can do this. A recommended methodology is to search for closed frequent item sets directly during the mining process. We can do the search process while the mining process is happening. This requires us to prune the search space as soon as we can identify the case of closed item sets during mining. We can identify the closed item sets and it requires some pruning process. We can use different pruning strategies for this. We can use item merging, sub-item set pruning, or we can use item skipping. Item merging, if every transaction containing a frequent item set X also contains an item set Y, but not any proper superset of Y, then X union Y forms a frequent closed item set and there is no need to search for any item set containing X but not Y. So this is one condition for pruning that will help the search for closed frequent item sets. Another method is sub-item set pruning. If a frequent item set X is a proper subset of an already found frequent closed item set Y and support count is also equal, then X and all of X descendants in the set enumeration tree cannot be frequent closed item sets and thus can be pruned. And the other method is item skipping. In the depth first mining of closed item sets at each level, there will be a prefixed item set X associated with a header table and projected database. If a local frequent item P has the same support in several header tables at different levels, we can safely prune P from the header tables at higher levels. So if we have a same support count for a particular item at a different header tables and in different levels, we will prune that from the header tables at higher levels. So these are the different pruning strategies that can be used with this particular methodology. When a new frequent item set is derived, it is necessary to perform two kinds of closure checking. So after finding the frequent item set, we will do some closure checking. First one is superset checking and the second one is subset checking. So in superset checking, checks if this new frequent item set is a superset of some already found closed item sets with the same support. And subset checking checks whether the newly found item set is a subset of an already found closed item set with the same support. To assist in subset checking, a compressed pattern tree can be constructed to maintain the set of closed item sets mined so far. Based on this property, a two-level hash index structure can be built for fast accessing of the pattern tree. So this is a method that can be used to avoid all the frequent item set, or we can see only the closed frequent item sets, which will be very helpful for the mining the actually needed frequent items.